very low frequencies. And hi, welcome. And we want to do something around 60 megahertz, and we want to go really deep at 150 megahertz, all sky, and then extremely deep. And so this plan, with slight modifications, was from the beginning. But my goodness, you can make plans because you know the sensitivity of the station, and then you can draw nice sensitivity diagrams like this. But it turned out to be really hard to go from plan to reality. And basically, we're still working on this, on how to deal with the data. And many people here were involved in getting that. I think that the main institute is Astron. Basically, that's an institute that basically is geared towards building radio telescopes. So they've been operating in building Westerbork, now LOFAR, and they're keen to be involved in SKA. But we have a big survey team all over Europe, but also some people outside Europe that really contribute to all kinds of stuff, either techniques or the science or whatever. And it was hard. And all the bullet points here, took a few years or more. Our fire rejection, I think that's completely under control now. It's automatic and fine. Not so much a problem at 150 megahertz, but low front to this. It turns out that our clocks were not good. So they were drifting all the time. If you did deformity, it's not good. So we need to find ways to solve that, which we've done. We've got really large telescopes in terms of side lobes and beams. So anytime there's a bright source in the side lobe, it's panic. If cygnus A is one of the side lobes, it dominates the signal, which is not handy. All kinds of stuff with calibration, imaging, etc. And we needed the whole framework to do this on. I think the biggest problem was the ionosphere. So the problem is more or less if you lay at the bottom of a swimming pool and you want an image of that cloud. That's hard. What you see to the left is what some people show a scary movie, where I think the time resolution is 30 seconds. And what you basically see is at low resolution, you see what's happening if you don't do proper calibration and you, at very low frequencies, you follow the sources. So what you then have is a beam of 3 by 3 or 3.5 by 3.5 degrees, where in, let's say, 30 independent patches sources move up and down. Yeah? And moving up and down is a few odd minutes, timescales of minutes at 150 megahertz, and you need to all put it down. So I know there's also optical people here. So it's a little bit similar to optical interferometry, where people do that here. They know what the coherence volume is, and the whole point is that in optical interferometry, you have a coherence volume, it's defined by time, which then is milliseconds, and then on the sky, which is a few seconds, and then you need to have enough information in a volume to be able to calibrate an optical interferometer. Well, here we have more like patches of 10 to 30 odd minutes, timescales of a few minutes, and we have to have enough information in there to be able to calibrate. Over the years, we've developed with Astron all kinds of subsystem pipelines, etc. And that's too much to go into detail here. But the main thing, I think that's credit to Reinhard van Reeren, who wrote a beautiful paper in 2016 on this. They basically, realized that, and there are a number of implementations now, where if you look at the LOFAR beam, there are those patches, and then you basically need to find a bright source in each of those. You find the 20 brighter sources, you find with the 400 distillation patches around them, and then you basically need to self-calibrate each of those patches and glue them together. And many of you know how self-calibration works. And the self-calibration towards each patch gives you then the phase solutions, and that then helps you to make images. Well, the first papers published by Tim Schimmer on the survey were kind of at the quality you see up there to the left. because we simply didn't know how to do that. And now we kind of have solved the whole thing, and out comes automatically images like that. What's kind of nice is that this whole thing also works for Meerkat. So Andrea Bottione and Reinhard van Leer have worked on this the last few months, and they can make images there. And what you see here is a Meerkat, and that you see in red, which is not really obvious, kind of like the facet definition for a Meerkat observation. So this is the first image we produced, and you can't really do justice to it because the field of view of LOFAR is enormous, but they say 3 by 3, 3.5 by 3.5 degrees. So you need 400 of those screens here to properly see what's in the data. One nice way, and this is work by Wendy Williams, who basically was a very, very good student that came to do a PhD with us. Thanks for that. This is MVSS. This is first. It's the same field. And of course, what you see here is that the point with MVSS is that it's very good in capturing the large-scale image. And first, the high frequencies. And what we do with our surveys, you capture both. This is a standard 8-hour observation. And you basically try to do this all sky, and I've covered something like 80% of the northern sky. Yeah, some nice images coming out of this. This is all for free. You can download it and do science. You also see sometimes very special stuff. This is an AGN, a cluster that we published. And this is where we are now with the 150 megahertz lot survey. We covered a large fraction of the northern sky. And we're now basically filling up the collective plane. But using radio data in collective plane is not easy. So the next step is, really busy, we have a number of papers out now, is going deep. And we're going deep on the 4 famous fields, and especially the Euclid deep field. North is very important at the moment. And the noise levels we're aiming at is a bit better than around 10 microjenskis, which is 150 megahertz, really deep. And then collectively, it will be something like 30, 40 square degrees, which is phenomenal at this depth. And again, you can almost say that 10 microjensky at 150 is 1 microjensky at Albert. So it's really nice over such enormous areas. And you see here an image there. So that's the second thing. And the other thing, of course, is can we use the long baselines? 6 arc seconds, 2 arc seconds. And the answer is yes, we can, but it's really hard. This is the Alliance field. If you zoom in. This is 6 arc seconds. And the step from 6 arc seconds to 0.3 arc seconds is enormous. So this is basically, go from here to here. Or, and I'm not sure, this is the 6 arc seconds, and then you go to 0.3, 6.3, and this is better to see. Where you see the inserts 5 arc seconds, and then, we only have now 1 published image on this, and the reason is that doing this is computational phenomenal. I mean, 1 image at 0.3 arc seconds has twice the number of pixels as the whole first survey. It's you got 2.5 degrees, pixels 0.1 arc seconds, and you have all those facets, etc. We need to go to the National Compute Center. I mean, it's 250,000 CPU hours to basically do with 1 image of 8 hours. But with the whole northern sky at 0.3, we'd like to do a few thousand hours at 0.3 arc seconds because they're reaching SK8 depths. And which would be around microjensky, correct, which is 0.1 microjensky in L-band, roughly speaking, so it's phenomenal. So, just a cute image. I can't talk about science, but this is what you can do. Roland Timmermans just finished. And, so, HVA from 6 arc seconds to 0.3. We have a team working on this and we're making great progress. I'm amazed that this is possible. Then Francesco de Gasperin has been doing a lot of work on also trying to do the LBA. This is 50 megahertz, and the first data releases were crap, and now he's really mastered it, where noise levels of typically milligensky per beam, which at 50 megahertz is really good, and he's now mapped something like 25% of the northern sky with this. Another big challenge, and I should credit, so he's on the next page, Reiner van Weeren here, is can we do things like 20 megahertz? And so we've taken lots of data and basically data for the whole northern sky. But this was hard stuff because I showed you the ionosphere at 150 megahertz, and if you extrapolate that to 30, 20 megahertz, sky is hell. But this great PhD student, Christian Groeneveld, basically now has done 2 fields, really depth reading, submitted to Nature Astronomy. And it's now under review there. But you see, I mean, the previous HC is the best there is, and then we're going lower and to high resolution. So fantastic. Give a little bit more on this. Can someone mute? Because okay, yeah. To give an idea here, and you see here, you see all kinds of point sources, but here and there, things that diffuse. And yes, you can really see there's I think a cluster there, and this one too. So this slowly starts to work. This gives my status. But like all radio astronomers know that continuing radio surveys are relatively useless if you don't do lots of optical stuff. And so we've been engaged as a team, as a country, etc. So we've done a lot of work on optical identification, how to do that, because it's complicated. We built a global Galaxy zoo, which also now people are using here, and we use the whole complete machine learning pipeline to do the identification, which is really good fun. I don't want to talk about that in detail. At Perfect Postdoc, Ken Duncan, we've done lots of work on the redshift, especially geared toward those kind of radio samples. And we have also a lot of work on source classification. The latest data release for LOFAR, DR2, basically has for 4.5 million sources the identifications, also the photometric redshift, the classification. And it's really nice. The big step now we're doing in the optical is we're about to start the brief LOFAR survey. The plan is.
Just close this. I don't know, it appears something.
Okay, yeah. We take a million spectra of the brighter LOFAR surveys to take. And that have many goals, but one of the goals is to find high redshift radio galaxies. I hope we get a few of them bright enough to do 21 centimeter absorption spectroscopy with LOFAR, and then hopefully learn something about EOR. The other big thing, and some of us, including me, have been involved from the very beginning, part of the Euclid Consortium board, we've been sharing it, was Euclid. And Euclid was launched with a SpaceX satellite, but because we were first going with a Russian one, but somehow that wasn't possible anymore. Was launched last July, and so it was in commissioning mode for the last half year since then. There were a range of issues, but they basically all have been solved. And the fantastic news is that the big Euclid survey has started 2 weeks ago. And that basically means that it will map 40,000 square degrees. It gets, I don't know, a billion galaxies in AGM. I think the combination of meerkat surveys LOFAR surveys plus Euclid will be phenomenal. So far, we produced a lot of papers. This counting is a half-year old, so sorry for that. And then if you look at the survey papers, I mean, there are clusters in HGN, miscellaneous. Even we found that M dwarfs, a good number of them, 10 or 20, have you can only see in polarized light, in circular polarized light, which caused quite a stir in that community, which is good fun, completely unexpected. And then with such a survey, you can either do big statistical stuff, which is nice, but also really kind of like take the data and publish individual ones. We just had a paper out on 10,000 giants, sizes over 700 kiloparsec. The biggest one, 5 megaparsec. So this is my 20 minutes on LOFAR, but yeah, I'm also a scientist, so I'm trying to go through a lot of scientific highlights, and I'll talk about HGN and cluster of galaxies, and then I'll probably stop before I do the start from galaxies because it's simply too much. But if you want to talk to me about that, just come find me, and I can just show you the slides. Okay, radio HGN science. Lots of questions, lots of issues. You can have whole conferences on this. But it's the life cycle. So you'd like to know something about the host galaxy, and you'd like to know something about the feedback. And I'll give some highlights on all of them. What is nice about the life cycle is that LOFAR is very good at detecting all plasma. So shorts get bigger and bigger and bigger, especially the FO1s here. And what I'm now going to do is something really unfair, because I'm going to show an old VLA image overlaid on a LOFAR image, but it basically dramatically shows why for studying long lifetimes in especially FO1 radio sources and also other phenomena, LOFAR are important. So this is basically an image by Van Bruegel. And then if you then overlay a 50 megahertz LOFAR image, then this basically you can suddenly see instead of a small source, it's dramatic. It's well over a megaparsec. And of course, this is a source within a not very massive cluster. You see the Chandra images, and but you can see over what time lifetime and what impact this has on feedback. Now, what is nice is because you have such a powerful machine, so many sources with all identification. You can make what people call a PD diagram, a power size diagram for a lot of sources. This is a very nice paper by Martin Hardcastle of the first data release, DR1, where he took, I think his redshift cut was 0.3 here. And then you see the old classical 3C sources. And then you see basically in those dots an indication how many sources there are. And what you see is the resolved ones are green and the unresolved ones are blue. And what's really nice is that you can start fitting models. You see those models there. And then you can do integrate those models and start getting an idea on the power input from those collective HGNs onto the galaxy, which is important for feedback. This is the biggest one we found so far, although we have one that is not on 2 megaparsecs bigger. But yeah, it's a journal where they say we can't talk about it before it's published. And this is one of our students, Martijn Boei. And it's a phenomenal beast with 5 megaparsec. Okay. So if you think about this field, you ask yourself, okay, those radio sources are nice, but maybe especially optical astronomers has in mind, what is almost scared because those beasts are rare. You've got elliptical galaxies. Those are the pieces we should study. And those radio sources, yeah, here, there's elliptical that has some radio emission. Okay, that's his problem or her problem, whatever. But one of the papers, this was led by José Sabater, is that if you do a careful job of taking those fairly deep data and then do from 0 to 0.3, and this the data is 1, and then try to see, okay, what fraction of them has a radio source as a stellar mass? The, to me, surprising answer, but if you really look at literature, some of this was known, is all of them. So all ellipticals that are massive have a radio source. And that's what you see here. The fraction is mass. And if you, not all of them have a very luminous one, those are 25. But if you go to the 22 or 21.5 regime, they're just all there. So the idea is that massive galaxies sometimes are off, and maybe not all the time are off, maybe 5 to 10% are on, simply incorrect. They're always on. The other thing which was nice was there is the classical view on radio loud versus radio quiet for quasars. 10% is radio loud, and there are funny parameters like what's it, the R5000, etc. And we found that basically quasars, to the depth we're looking at, we see 30% of the quasars, and we don't see any two populations, just a continuum. And I should have Kabi Rivera just submitted the paper looking at the quasars at deep field, and she basically sees all the quasars. Yeah? So the whole idea of that quasars, some are really loud, some are really quiet, is just incorrect. And if you go deep enough, you see all of them, just continue. Yeah? Now, what's very interesting, if you know that, you can basically really help with distant quasar searches. Because there might be people do optical or infrared searches, then people search for distant quasars, and that's really painful. And we also probably do that with Euclid. And yeah, you basically look for really red objects with colors so that it breaks trails, and you get things that are 6, 7, 8. And then you start to take spectra, and you have a success rate of maybe 1%, 2%, 3%. So you spend an enormous amount of telescope time. But if you, with this kind of reason, you have a radio prior, we've got something really red, plus a radio detection, your success rate suddenly goes to 30, 40%. A very nice PhD student working on this, Annie Blaudemanns, with Johan Abi and others. She did that, and taking breaks from the DESI plus LOFAR, she was able to find a beautiful sample of quasars. So for Euclid, this is something that probably, this is the plan for Euclid, to get to 6 and 8. First instance, we'll just do spectroscopy of those ones that are radio loud, which then hopefully the success rate will go up. Okay, so what we observed is that massive galaxies are always active, and there's no dichotomy for quasars. Yeah, and this has lots of implications, and talk about it for a long time, which would be good fun. For feedback, it basically means that models need to take into account that radio feedback is always happening, instead of just it will go up and down, but that's important. And also, it's interesting to discuss with a number of people. There's always been the spin paradigm. Okay, why things radio loud and why are things radio quiet? Because some objects have a spin and others not. Well, look, if they're always radio loud and on, then the idea that radio loudness couples to spin is probably not correct. So I think that's a very interesting one. Okay. The other thing that is really good fun is study the PhD thesis of Shushan Zheng was with me for 4 years. Well, it's COVID time, so I'm sure you can see that. He's now a very nice postdoc in Shanghai. And what he has done, and I'd like to show you some results, is okay, you've got now those big samples of radio sources, also big optical surveys. Can we do a next nice step in connecting the properties of the radio sources to the properties of the host galaxy? Clearly a combined optical. And let me show you a few quick results. This is an interesting plot, because for a sample of fairly nearby radio sources up to redshift 0.3, where we had very good information from DESI and others for the redshifts, mass estimates, etc. We basically studied, first of all, the projected axis ratio. So if you take a spiral galaxy, it would be 0.2, 0.4. If you take a round elliptical, it would be 1. And basically plot the projected axis ratio versus radioluminosity. What we now find is that the very powerful radio sources, they all seem to be in galaxies that are fairly round. And if you're basically less powerful, you have a range of shapes. Keep that in mind. The second thing we could do is there's the beautiful manga survey. Manga is amazing because it makes basically, with fiber bundles, it can map the SADs spatially with a resolution of the order of kiloparsec of nearby galaxies. And they've done 10,000 of them, and 300 of them have a radio source. We also combined MTSS first, then because we want to have a range of powers. And what you then see here is sort of low angular momentum, the velocity field is a mess. And with high angular momentum, you have something rotating, and the velocity field is beautiful. Unless you like a mess, then it's also beautiful. So what we now plotted there in mass bins, left, middle, right. So from massive, very massive, really massive. We plotted radio luminosity as a function of angular momentum. What's interesting, especially in the higher mass bin, is that what you see there is that there's a preference for radial loudness to be associated with galaxies with low angular momentum. And they're always, So that's an interesting general statement, which is nice to see. Simply comes out of the data. The data exists. Okay, and the final result for my thesis was that if you think of radio sources, they've got beautiful jets, hotspots, lobes. They've got something in the middle, the host, from the elliptical, very rarely spiral. And that host, basically, you can define axis, you can major axis, minor axis. We study basically the relation between the direction of the jet and the direction of the major or minor axis. What we found, and that is shown here, is that what we see is that the jets seem to be aligned along the minor axis. And so in this thesis, it's all published, so you can look at the papers. We basically found 3 or 4 things. So the luminous radio sources tend to be in the round and massive galaxies. The host of luminous radio sources have low angular momentum. Radio sources tend to be aligned with minor axis. And I didn't show you that this minor axis alignment is more prominent for sources that are large. So sources, if you look at the diagram for sources bigger than 250 kiloparsec, say, so the big ones, you see even better alignment than for the ones that are smaller. So again, I can talk a lot on how to interpret this, but if you think about how galaxies form. There are two major pathways. You have a blob of gas, and that blob of gas shrinks to the center and you form a spiral. And you get a spiral galaxy. The other one is that you basically have a few spiral galaxies, you collapse together and you get a massive elliptical. So we feel that this picture links to those observed properties in the sense that the very luminous ones, they're associated with more massive black holes in massive galaxies, that they have that merging history, whereas the less luminous ones, they have still some kind of remembrance of their associated disks, and hence there's an alignment with the galaxy and the memory of the early accretion disk and also the spin of the black hole. So that's great. Agent feedback, show you some quick results. And pictures like this, where the jet somehow puts in a lot of information into the surrounding medium. This is a very nice picture, and you lay to the left, the LOFAR to the right, where you basically see in the X-ray, you see cavities. The idea is that those are basically holes in the X-ray, and somehow a radio lobe jet splout through, basically excavated that hole and also dumped in a lot of energy. And very simple models suggest that there's a balance between X-ray gas heating, losing energy due to cooling, and the balance is then the radio sort of violently heat, so that you keep the thing at temperature 10 to the 7 Kelvin. And we and other groups try to measure that relation between the radiant power and the cavity power. There's some kind of basic relation. So that if you take radio sources, and you take big samples, you can try to say, okay, hence if you have a survey that constitutes so much energy in total, energy per source times the number of sources you have, possibly as a function of redshift. And with that, we, or especially Robert Contepelli and Edinburgh's been making models for all kinds of sources, where he tries to then, and I won't discuss that in detail, where he then tries to see how much energy input, heating rate, there is in the universe per co-moving volume, per luminosity, and that's what you see here. And this also shows that this kind of heating is really important to maintain the feedback cycle of galaxies. Okay. This is on the AGN. And so if you go a little bit fast, but if you're an AGN person, you basically see the highlights and clusters, colliding clusters. This is also a bit of an obscure topic. Maybe 10 years ago, I think with LOFAR and EPOch and also the connection to X-rays, it's really kind of like is helping to understand clusters. And the idea is that if you have two clusters and you collide them, and then you look at the X-ray gas, what you then get is that in that collision you get turbulent gas in the center, and you get outward shocks, and those outward shocks they basically would have Mach numbers of 2, 3, 4, 5, and they would accelerate particles from the thermal pool for previous AGN. And that particle acceleration would then lead to kind of like radio emission, which you see there. Well, this was kind of theory, and what I'm now going to show you is also utterly unfair, but it makes a nice visual impression, which I like. This is an old node by Leiden de Bruin. It was absolutely instrumental to also get LOFAR off the ground. And this was an image he sent to us a long time ago on the when we do the wind survey. And yeah, it's not an interesting cluster, interesting structure, maybe a head tail. If you zoom in, it's it. And I think in 2015, I asked a very good Vietnamese student, Duan Huang, to make a LOFAR image of this, knowing this was going to be very difficult if in the middle of all that facet calibration stuff. This was his first result. Why was, well, you see there, that's by 8 degrees away, 10 degrees away with thickness A. And yeah, if you look carefully, yeah, you see the cluster, but it was, I was kind of feeling guilty to ask someone to work on this. But he managed. So this was basically what Westerbork 3 kilometers give you. And this is what the combination of facet calibration and LOFAR was giving you. Yeah? Which is fantastic. And this is also not really the way it went, but I mean, so the idea is this is a shock coming from a double merger moving outwards. And what was really fascinating, and you might have seen this, if you also observe the GMRT, the delay, etc. If you then make a spectral index map, this is the result. Yeah? So there is relatively flat spectral index in front of, no, at the shock location. And then if you then let the shock continue, particles lose energy and the spectrum gets steeper. And that's what you see here. So you can probably see the signs well before. But it was a beautiful illustration that shocks and clusters exist, are accelerated, etc., etc. And yeah, you call it the social cluster. Lots of people worked on this now, but now 60, 70 papers on this object. So everybody makes mistakes. Let's skip all the details because the shocks turned out to be really complicated. Also, the polarization structure is really nice. And but again, this is the big image of the system, where they see the full field of view, and they see the shock at one and the other, and then merely see a channel image of the colliding cluster, which I think is, if you zoom up, a beautiful illustration of power of X-rays, where you see the merging cluster and also the radio of the shocks coming out. Yeah, Julius Donnert, posted to me, did a fantastic paper on really getting all the physical parameters out there, and I think that's almost a separate colloquium how to do that, which you're not going to do. Yeah, you can get the orientation of the thing, because if you only see this if the shock is basically in the plane of the sky, so you can get all kinds of parameters there, and you get magnetic fields, shock parameters, so that's all cool. Okay, then what next in the cluster area? I'll show you some results. We discovered that some clusters, there are bridges between two clusters. We could detect that. We saw in a few clusters that if you look at this one at 60 megahertz, and then there's very old plasma within clusters. And this is a spectral index of -4. Yes? Basically means it's invisible with NIRCad. Because -4 spectral index means that if you can rarely see it here, it's a factor 10,000 fainter at NIRCad or at LDET. And what we say here is that, some clusters are full of old plasma you don't see, old radio plasma, and only at very low frequency you can see that. And especially it might be re-energized, some turbulence, and you can see it at very low frequencies. Okay. This is very good fun, and I'll stop. This is what we basically now know if you look at an X-ray cluster, and this is 2255, and which in the X-ray is kind of a normal, okay cluster. You see it here. And for a number of reasons, we thought, let's go really deep on this cluster and then see whether we see the halo, we see the relic, but we can also see parts of the filaments, which is very important because then we can measure magnetic fields of the filaments, brainstorm where that could come from, those magnetic fields, etc., etc. So, yeah. And this is basically what you see is that if you go deep enough on this one, and this is, what is it, 80 hours of LOFAR, the whole field is full of filaments, shocks. You can see that high resolution. And then if you go, there's a LOFAR, we have also very good surface brightness sensitivity due to many stations in the center. You can see it's completely full of shock material, and, which is nice. Okay, final 2 slides, and then I stop. Is wow, we've learned a lot from magnetic fields, particle acceleration, nearby clusters. And if you look at some models, they say, well, we shouldn't see this at high redshift, where high is 1, because clusters are forming then, and according to some magnetic field acceleration models, you need just time for clusters to develop magnetic field. And this is from a paper by Faka, where basically the idea is that, yeah, at redshift 1 or so, there should not be a lot of magnetic field at redshift 0. To our surprise, there was a really nice thesis by Gabriela and Canaro 4 years ago. We found when she looked at a sample of Planck clusters beyond redshift point C, that half of her objects were had those diffuse radiation. And this is simply looking at the existing data in 8 hours. So that was great. And yeah, basically this helps understanding where the magnetic fields came from. And yes, they also existed at redshift 1. Okay, let me stop here because then we can ask some questions. And if you to do. I'll skip the cosmic star formation rate history, but the blue dots are LOFAR deep fields, so we can really map that out. We see that. Go to back, because then we have 10 minutes left for questions. And if people want to know about LOFAR and star forming galaxies, yeah, just talk to me and I'll show you the slides. So I think the bottom line is LOFAR is doing great. Thanks for your attention.
Thank you. Great talk. Any question online? Yes, Leonard.
Yeah, I find it really interesting that you see similar magnetic fields, same at redshift 1. How surprising is that? Because I would definitely expect maybe to go to an even higher redshift. At some point, we would see an evolution, right? Any comment on that a little bit more? What are the ideas behind it? And maybe if we even go to redshift 2 or 3, is there something that we can expect to change?
We can't expect to change it. It's a difficult question in the sense that I think if you, and I'm not an ultimate expert on that, but there are a number of ways people form magnetic fields. Yeah. One of which is just outflow from Star galaxies. Yeah? And if you believe that, that might not be overly surprised because outflow is also connected to, for example, metallicity clusters. Yeah. Because it's a similar process. And then I don't think we've, and also the clusters for which we have metallicity measurements, they're not so dissimilar from local. So in that sense, you might expect that. Yeah. If there are models that basically need some kind of seed magnetic field and then need to grow up by either compressing the magnetic field or amplifying that by turbulent amplification, then you would kind of like expect a constant growing magnetic field, and then this is getting slowly uncomfortably high.
One follow-up question. So I'm saying the star formation rate would influence it, but then you would see the dependence, some, I don't know, peak or minimal ground relative to or something like that, if that would be the case. But it's still correctly?
Well, I think the idea is that once you produce magnetic field, it just stays there. And it starts form and then star formation stops. So it's like metallicity in a cluster.
Okay.
The injection might peak at redshift 1 or 2, but then once you've injected, you basically then it has a certain metallicity and it stays like that.
Yeah.
Yeah.
More question. Yes.
You had silent star formation, it's kind of being pursued. Yeah.
This one, yeah.
Yes. And the one next to the one after, actually.
Yeah. Okay. So what Dan Smith and also one or two other papers found is that what you there see to the left is the famous relation between radio emission and star formation rate, where we have tried to be very careful to exclude all the HN, yeah, which is not easy, but okay. We try to do that either by using standard diagnostics. We also, but not for this sample, try to do that with high resolution LOFAR observations, but we don't have that for this whole sample. And yeah, you get the standard relation back. But what's very nice is that we see that this relation is dependent on the mass. So, and that's basically to the left here, where you see mass versus radioluminosity in various colors and different scales, and where you see that mass plays an influence there. And I think we have no clue why. Yeah, there are some ideas, but not, yeah. Okay.
Okay. Any question online? Yeah.
Question. Then what's the future for LOFAR?
Sorry?
What's the future of LOFAR? Is there plan to eventually expand this with some more?
Oh, that's also a good question. So lots of plans. I think that the immediate timescale, we'd like to really learn how to routinely do those long baselines so that we can do many more images. Also like to learn how we use the long baselines to go to lower frequencies. Then the next step is to something that's called LOFAR 2.0, which is now being installed, where you'll have more beams. You'll have a white rabbit system so that the clocks are stable. And at the moment for the Dutch stations, we only use 48 dipoles. We observe below 80 megahertz, and that will then change from 48 to 96, which you really hope with calibration. On the longer time scales, there are all kinds of plans. One plan is, and that's probably the first big step, is to get new dipoles. Because if you look at the sensitivity of LOFAR at the low frequencies, there's not really much sensitivity, 10 megahertz, and then it peaks at 60 and then drops down to 60. And part because of that, if you have those dipoles, they're basically so packed together that they sample same parts of the electric field that's coming in. So having somewhat bigger dipoles spread them further around should give us much more sensitivity. And then we can focus towards really make sensitive images at 10, 20 megahertz. And then, for example, George Miley has a I would call it even a plan, but more like an idea that it would be great to have some stations on another part of Africa to go from 0.3 arcseconds to maybe 0.1 arcsecond. That never sounds like a big step, but in practice it's a factor of 10 better. So because it's squared. would be great too. Yeah, and then ultimately, I think we're really computer limited. So personally, I think we come to do the projects behind the layer mode to the best. Hopefully, we get 3,000 hours in elliptic field, and we get that around 1 microjensky at 50 megahertz. But I wouldn't mind doing that all sky, and it's just simply find the computers, because in every step we throw away data simply because we can't handle it. But maybe in 10 years, this is something we could do.
On the slide where you're discussing the deep field observations and the radio loud and quiet quasars, you mentioned that with the deep field observations, you can see all of the quasars.
Yeah.
And I was wondering, how do you know that you can see all of them? How do you know that you're not missing some? Are you comparing it to what was known before, that you already had radio loud and quiet identified, and then you?
No, it's the other way around. So you take optical surveys of plus the combination of Elias, Lockman, Bootes. You take the existing quasar surveys there, and then you see whether you can see them in the radio. And the answer is all of them.
Okay.
Just yeah, a bit surprising, but maybe overly surprising if you. But it's an interesting result. And the difficulty that people couldn't do that is because you could now very deep data over 30 square degrees, so you get a good sample of quasars. And in the past, if you then want to do that for a few hundred quasars, you basically need to have very deep integration time of all those quasars individually, and that's a project that probably near-cut to VLA would say, well, just observe a few quasars. And you don't get statistics for the statement.
Okay, I think we're almost out of time. So thanks again. Let's thank you. See you in the next one.
Okay, thanks for coming.